Okay, so we're going to continue. Okay, then we talk about the first part, which is how the objective function coefficient change. Okay, so you know that that's the allowable increase, decrease, and there is special situation, which is when there is a zero, that it's indication of alternative solution exists. Okay, next, oops, sorry. Look at impact on the optimal objective function value of changes in the constrained resources. Okay. So the shadow price is something we're going to introduce, and if we'll just read this first. A shadow price of a constraint indicates the amount by which the objective function value will change. Okay, given a unit increase in the right-hand side value of the constraint, assuming all other coefficients remain constant. Okay, so you can see now we're looking at impact on the object function value. It's no longer about the solution. Okay, and it's talking about the right-hand side value. And we talk about like there are some binding constraint and a non-binding constraint. We know that for those binding constraint, because all the resources are used up. Okay, so left-hand side equals the right-hand side. That's why our optimal function value cannot continue to improve, because if you think about that graphical solution, if you continue to improve that, continue to move that level curve, you are out of the feasible region, right? But if those right-hand side of the constraint can be loosened, which means, okay, the feasible region can be enlarged, then you may be able to keep moving that level curve to that desired direction. So your object function value keep increase. Okay, then let's go to the here. Where's my note? Here. So now we are talking about this part. Okay, so here, these are the allowable increase of decrease of the right-hand side of your constraint for the shadow price to remain the same. Okay, so similar pattern. Okay, so you can remember this as in the second table. The third table. The third table is about constraint, and this allowable increase and decrease are the amount of those right-hand side value can change without changing the shadow price. We'll just read the definition of the shadow price, and we'll talk about how to use the shadow price later. Okay, but for those shadow price to remain to be the same, the right-hand side value change should be within the allowable increase or decrease. Okay, which means, for example, we have the pump constraint, right? X1 plus X2 need to be less than or equal to 200. That's the first constraint here. And this right-hand side can change to 174 to 207. Can go within this range. That's the shadow price of, I think that's the pump, will remain to be 200, which is this value here. Okay, so the shadow price of pump will remain to be 200 only when the right-hand side changes within this range. In other words, if the right-hand side changes without those range, then we don't know what their shadow price is, and then we won't know what's the impact on the objective function value. Okay, so that's the allowable increase, decrease in this second table. Remember, it's for the shadow price to remain to be the same. It's not for the option. It's not for the optimal solution to be remain the same. Okay, so if you remember, both table is kind of like, okay, it's only of this side for this value to be the same. This is for these values of those values for these values to be the same. Okay. Then we'll look at the shadow price. So here are the shadow price, and we'll go back to the slide. That's what we're talking about. Okay, so the slide says it's the objective function value changes when 1 unit of increase in the right hand side change. Okay. And the shadow price for non-bounding constraint are always 0, because the shadow price is about the impact on your object function value, which means whether you can improve it or not. And if a constraint is non-binding, which means you already have surplus, you have already some slack left. Like in that case, it's that the labor tubing. Yeah, tubing. We have 168 units of tubing left already. When you have more, it won't impact on your object function value at all. So the shadow price of that will be 0. Okay. Some comments. Shadow price only indicate the changes that occur in the object function value as the right-hand side change. Changing a right-hand side value for binding constraint also changes the feasible region. Okay, we can see this. To find the optimal solution after changing a binding right-hand side value, you must resolve the problem. Okay, remember, like in the previous part when we talk about the coefficients in the object function, we know that okay, the solution won't change, but the object function value will change, but we can calculate because the coefficient changed. Okay, in this case, we only know the impact on your object function value. Okay, so originally it's 66,100. That's the total profit, and from the shadow price we can know, okay, say if we have 1 more unit of labor, how much impact it will have on our total profit. But we won't know how many to make for equal spots or hydrolysis. For that part, we have to resolve the model to find out.
So the shadow price is basically the impact on your final value from your final solution of what you're going to get, like your minimize or maximize, but it doesn't tell you what units comprise.
Right. It won't tell you how many units to make. It only tell you how your objective function value is going to change. Okay. And we'll get to that too. That's it. So, for example, let me just run through this graphical solution so we get a better. Then, again, for simultaneous changes in the right-hand side, remember when we said it, the shadow price hold only when you change one of them, while the other coefficient remain to be the same. Okay. For all constrained right-hand side that changed, sum the percentage of the allowable increase and allowable decrease. If the sum of the percentage does not exceed 100%, then we know the shadow price will not change. So this is saying that if you have 3 constraints and you want to change 2 of them, the right-hand side of 2 of them, okay, whether you know the shadow price of these 2 will change depends on this 100% rule again. You sum the percentage of the change in regard to this allowable increase or decrease. If it's less than 100%, then you know the shadow price won't change. Then you will be able to use that shadow price. Okay, so some illustration how the right-hand side changes when. So originally this is our feasible region, and when we change the labor hour, which is the right-hand side, originally it's 1566 to 1728, and that's a new constraint is something like this. Originally it was this here, and when you increase the right-hand side, it moved to this direction, and so you see there is some additional area available for you to improve the optimal solution. Okay, and the level curve can move. Originally it was somewhere here yet, so it can continue move, and it hit this point. It gives you a better optimal solution. And we can find the intercept in this case and calculate what the objective function value is. Okay. So this is the graphical representation of how a certain right-hand side changes the optimal solution. Sorry, optimal solution as well as the total profit. Okay. So originally, oops, sorry. This labor hour is 1566, and when you change it to 17, the optimal solution moved to here. Okay, let me go back to this note again. Okay, so we talk about for those shadow price to remain to be the same, allowable increase decrease need to be. The change to the right hand side need to be within this. Okay, now let me ask you. Okay, now if this 200 value change to 205, okay, what is the new objective function value? Okay. What we know is that first we need to check whether this change is within the allowable increase. Okay, so from 200 to 205, that's 5 units of increase. Okay, and we find out, okay, the allowable increase is 7. So that means it is less than 7. Therefore, shadow price of 200 remain to be the same. Okay, and then we know that the shadow price is the impact on our objective function value given 1 unit of increase in your right hand side. So currently the new objective function value equals to be the old one, right? The current objective function value is 66,100. So 66,100 plus the impact. Okay, and this impact is for each unit of increase, the impact is 200. Now we have 5 units of increase. So that should be 200 times this 5 here. Okay, which gives us 1,000. So that's the new objective function value. Okay, then x1, x2 values have to be determined. Okay, if say the manager really wants to know what's the new solution, then you have to resolve the problem to get it. But if the manager is only because that's the objective, right? The objective is to maximize the profit. And in this case, the management probably is only interested in knowing, okay, is it worth to get more resource for those binding constraints? Okay, if it's worth, then let's do it. And then we'll just figure out a new solution. Okay, so it answers the first question, whether it's worth to get new resource. Okay, and we haven't answered that question yet. We only asked the first part. Okay, we know the impact. We know that, okay, the objective function value will increase. Okay, it will increase by 1,000 units. Okay, and in this case, $1,000. And if the extra if the extra price you pay for those extra resources is less than this $1,000, then it's worth buying, worth getting more resources. Okay, and then we'll talk about how to identify that here. So that's if we go back to, is this problem clear? Is this part clear? How to identify the impact? Now maybe I'll ask you another question. Okay. What's the new objective function value if we get more tubing? Currently we have 2,880 units of tubing. Let me get. Okay. So currently we have 2,880 units of tubing. What's the objective function value if we get 2,881? The same, okay? Why? Okay, good. Shadow price is 0, it's non-binding. We've already got some slack, which can be calculated by taking the difference between this value here and this value here. Okay, and if we look at just by looking at this sensitivity report, we can say, okay, the shadow price is 0. That means we can increase it here. See, we can increase it by to the infinity. Okay, so this value here represents infinity in Excel. Okay. So we can increase this right-hand side value to infinity, and the shadow price won't change because it's non-binding. You just keep increasing it, and it's not going to make any difference to your optimal solution. Okay, but if you decrease it to a certain degree, your shadow price will change. Does that make sense? Look at this value, this 168. What's that value? Do you guys remember that? That's the slack value, right? Okay, that's the difference between the left-hand side and the right-hand side. So it makes sense, right? If you decrease more than that amount, this constraint probably will become a binding constraint. Okay, and when it becomes a binding constraint, it will start to have a non-zero shadow price. So that means, okay, the shadow price will change. Okay, so it makes sense. So that's the shadow price. And we're going to look at one example here. Oops, already showing that. Okay, here. You may need to write this down. Okay, so there is a new hot tub, the third type. Okay, the Typhoon Lagoon is being considered. It generates a marginal profit of $320. Requires 1 pump, 8 hours of labor, 13 feet of tubing. And the shadow price of each of them is given. And they ask you whether it's profitable to produce any. So to think about this problem, I think about, okay, to determine whether it's profitable to produce any, we'll think about what's the impact on your objective function value, right? And what's the cost it takes. And in this one, you can think in this way, okay, so you have this, this resource pool here that's used to produce those aqueous baths and hydrolysis. Okay, and currently using those resources, which are the pumps, the labors, and the tubing. Okay, using those resources from this resource pool, you get this much. Okay, that's the total amount you're making. Okay, now to make this third type of hot tub, what you need to do is take some resource away from this resource pool, which were used to make this hydrolysis and aqueous bath. Okay, then we'll think about, okay, by taking away those resources to produce this new hot tub, what's the impact on my original total profit made? Okay, and what's the gain that add on top of this total profit? Okay, so let's look at it. by taking 1 unit of pump from that resource pool, the shadow price is 200. So when you decrease it, that means you're going to decrease the available resources, which is decrease the right-hand side that you use to produce equal spots and hydrolysis, right? By decreasing by 1 unit. Okay, you're going to take away 200 from your total profit. Does that make sense? You are taking away 1 unit of pump. So that means a decrease, 1 unit of decrease in the right-hand side of the first constraint. Clear? Okay. Then here, when you take away 8 hours of labor, that's again, you're taking 8 hours. So okay, 1 unit of pump, 8 hours of labor, and 13 feet. Just to produce 1 typhoon lagoon. Okay, so then this one, you're going to take away 8 hours, and each hour of labor is going to impact that your objective function by 6.67. So this is the total amount of impact on your objective function value. And this time we are subtracting because we're taking away, that is a decrease. Okay, and 13 feet of tubing, it's a 0, minus 0 times 13. Okay, and actually before we can do this, one thing we need to check. So go back here. Okay, so first thing we need to check is, okay, we want one pump, 8 hours of labor, and 13 feet. Okay, then we look at, okay, first 1 pump, allowable decrease here is 26, so that's within, within that allowable decrease. So this shadow price won't change. Okay, and this 8 hours, we're taking away 8 hours from this model here. Allowable decrease is 126. So this shadow price of 17, which is 16.67. Okay, won't change. And we're taking away 13 feet. Allowable decrease is 100. Okay, so shadow prices or whole. Actually, for this one, it's a simultaneous change. We need to use that 100% rule. So let's use 1 divided by this plus A divided by 160 plus 13 divided by. It is less than 100%. Okay, if we just take 1 out, it should be. Okay, so we have this 100%, so the shadow price will all hold. Okay, then I'm going to wipe those parts. Then we're going to look at the impact. Okay, so the original, actually we don't need to use this part. By taking away 1 pump, it's 1 multiply, it's a shadow price, 200. Minus, we have 8 hours, multiply the shadow price, 0.67, which is shown as 17 here. It rounded up. Minus 13 feet times the shadow price of 0. This gives us a value. You guys have a calculator? Or $300 what? 32.3. Okay.
No, sorry, 333.36.
333.36.
Yes.
Okay. Okay, so that's the total amount of money that we are taking away from here. So we're taking away negative 333.36. Okay, but this Typhoon Lagoon also makes some money, right? It says it makes $320, right? So we can, if we just produce one of them, we're taking away this much because of the resource. We won't have enough resource to make this 122 and 78. So the total profit will change, this minus this. Plus, we're going to add $320 to those total profit pool. So is it profitable? No, because the total amount of profits is going to decrease by $13, right? Okay, $13.36. Okay, so that means, okay, it's not profitable to make this third type. So this is how we calculate. We don't even need to use that original objective function value.